Okay, so today we're going to apply what we know um, about rigid body kinetics to rolling without slipping. We've done rolling without slipping in particle kinematics before, where we used it to calculate the velocities and accelerations of points on a wheel. But now we're going to actually be able to use what we know about the forces acting to figure out accelerations and things like that. Okay, and the basic idea is like this. So the basic kinetics of rolling without slipping. So let's say that this thing is, in general, it's going to be rolling along a surface that, could be at an incline, it could be horizontal. We're always going to use a coordinate system like this, just like we did when we did kinematics of rolling without slipping. Okay. And what are the loads acting? Okay, so there's the body. Well, there's always a weight force. So there's a weight force like that. And then there's also a normal force that's perpendicular to the surface. And there's one more thing going on that you might not think of right away. But notice if there was no horizontal force at that contact point, this thing wouldn't roll at all. Excuse me. It would just slide down, like, if this was a rock on an incline made of ice, it wouldn't roll, it would just slide straight down. And so the thing that makes it roll is that there's a friction force at that point of contact that's holding that, I can do that better, that's holding that point back. Okay. And we're not going to use coefficient of friction or anything like that. So we'll see how that comes up. But these are the loads that act when something is rolling without slipping. Okay, so the way I'm going to do this lecture is I'm going to first do this calculation as if this was a rock sliding down ice, assume that there's no friction. And, this is also the same as if that thing was a cart with small light wheels. And we're going to calculate the acceleration of that object sliding down the incline. Okay. Then what I'm going to do is do the kinetics of rolling without slipping, and we're going to see how different shapes of, always round, but different types of wheels, whether it's a disc or a ring or sphere, how these different types of rolling objects accelerate compared to the case where there's no friction. Okay, so we're going to compare all these to an object that's just sliding down the ramp with no friction. Okay, so I guess I'll draw it as a block just to make it clear that it's not rolling. I could have also drawn it with little wheels at the bottom. That would have meant the same thing. For any rolling or sliding problems, we use this coordinate system with the y-axis pointed straight out of the surface. So I'm going to use this coordinate system. And I'll start with a free body diagram. there's a weight force down, and I'll just call that mg, and there's a normal force up, not up, not opposite the weight, but out of the surface. Okay, and let's say that this ramp has an incline of theta. So in all the examples I'm going to do here, we're assuming that there's no other external forces except gravity, and gravity is what's pulling it down the hill. Okay, well, this, since there's no change in orientation, this we can just do as particle kinetics. And so this problem is pretty quick and easy. You've done problems like this. So Newton's second law says, in this coordinate system, we have the normal force. And then we have to figure out the components of the weight force. You could do that as a 270 plus theta degree angle and use cosine and sine. The math comes out simpler if you do the trigonometry of the right triangle. And so in that case, this comes out to be mg sine of theta negative mg cosine of theta, just using SOHCAHTOA. And all that is equal to the mass times, we know the acceleration is along the surface, so like this. And if all we're trying to figure out is the acceleration, so we're trying to figure out the component, the x component of that acceleration, then we have mg sine theta is equal to ma, solve for a, and you get g sine theta. Okay, and so this thing is accelerating down the ramp with a magnitude of acceleration of g sine theta. Okay, so that's what we're going to compare rolling without slipping to. And ask yourself now, what do you think is going to happen? For the rolling problems, is it going to be a greater acceleration or a smaller acceleration than this? Well, the answer really comes from the fact that when something is rolling, we have this additional backwards force. So if the thing pulling it down the hill is still just mg, and the thing fighting that, there's a thing fighting that now, we're going to get a smaller acceleration. So rolling objects always have a smaller acceleration than an object that's sliding without friction. Okay, so now let's go to the kinetics of rolling without slipping, and we're going to compare our answer to this. We expect the acceleration to be smaller than this in every case. And I'm going to start by giving you moments of inertia for a few different shapes. So a disk, the moment of inertia about its center of mass is 1/2 m times the radius of the disk squared. A sphere has a moment of inertia about its center of mass of 2/5 mr squared. A thin ring, so that's where the outside edge of this ring, you could also think of this as a cylinder, is very narrow. There's not a big difference between the outer radius and the inner radius. And that is a moment of inertia about its center of mass of mr squared. And then I'll call it a thick ring, where we have to consider the difference between the inner radius and the outer radius. Has a moment of inertia about its center of mass of 1/2 times the mass times the quantity outer radius squared plus inner radius squared. Okay, well, notice that the thick ring formula reduces to the thin ring formula as the inner radius limits to the outer radius, so that makes sense. So the way I'm going to do this calculation is I'm going to assume that there's a mass moment of inertia about the center of mass. I'm just going to call it I. And then we're going to come up with a formula that has I in it, and we can substitute these values in at the end. Okay, so we're going to assume our rolling object has a mass moment of inertia about the center of mass that's equal to I. Okay, that's going to come up in our final formula, and then we can plug in whichever one of these to compare our acceleration to each other, or to compare it to the acceleration of the sliding object with no friction. Okay, so let's do the kinetics. Well, first of all, the examples that we've done so far have always had, the rigid body has always had a fixed point, okay? In this case, there's no point on the object that we're considering, this wheel, that's fixed. There is a point that has zero velocity at every instant, but it doesn't have zero acceleration. So it's not a fixed point, okay? So no fixed point. On the wheel means that we have to use our about point as the wheel's center of mass. If you go back and look at the rotational version of Newton's second law, that's part of it, is that there are only two possible places where you can choose your about point. You can choose it at a fixed point, and you want to do that whenever you have a fixed point. But if you don't have a fixed point, it has to be at the object's center of mass. Okay, and so that means that our mass moment of inertia is going to be about the center of mass, and so it's just going to be what we're calling I. Okay. So this is our about point for calculating our moments, and it's our about point for calculating the mass moment of inertia. So now let's go to the free body diagram. And here's our object. There's the center of mass. We have a weight force acting down. At the contact point, we have a normal force, and we have a friction force. Okay. And we're going to use Newton's second law and rotational Newton's second law. So Newton's second law says we have this force 0n. Again, we're using that rotated coordinate system. We have the friction force, which is negative FF0. And then we have that weight force, which we can represent the same way as we did before. This is mg sine theta, negative mg cosine theta. Again, that just comes from SOHCAHTOA doing the trigonometry. And this is equal to the mass of the object times the acceleration of its center of mass. Okay, and we're just going to call the acceleration of the center of mass A. We don't care about that normal force, so again, we just get one useful equation out of this to start. It says negative FF. I'm going to get all the variables on one side and move the mg sine theta to the other side, because really that's a constant. Those are not things we're trying to calculate, those things that are given in the problem. So negative FF minus mass times acceleration is equal to negative mg sine theta. And that's going to be our first equation. We can't solve for either of these variables, acceleration or the force of friction, because we only have one equation for two variables. But we will be able to put this into a system shortly, and solve for this. Now the moment equation. So this is the part that's different than particle kinetics. Well, we have to calculate the moments of all these forces about the center of mass, since there's no fixed point, and our moment of inertia has to be about the center of mass. Okay, that's no problem, because that's the variables, that's what we're given at the beginning, is that mass moment of inertia I. All right, so if the about point is the center of mass, what's the moment produced by the weight force? Well, that weight force acts at the center of mass, so it doesn't produce any moment about the center of mass. What's the moment produced by the normal force? The line of action of that normal force goes right through the center of mass, so again, that produces no moment. Okay, so far it's easy. But the friction force does produce a moment about the center of mass. And so we have to figure out what's the distance from that friction force, the line of action of that friction force, to the about point, which is the center of mass. And you can see that this dotted red line that I drew is perpendicular to that force of friction. And that's just the radius. That distance is just the radius of the wheel. So the magnitude of this moment is just FF times R, okay? But we have to think about the sign, so I'll put this in as plus or minus, and then I'll write this as R, force of friction. And now think about if the hinge for this object is at the center of mass, would the force of friction make it rotate clockwise or counterclockwise? In this case, it's clockwise, so we want the negative. And all this is equal to the mass moment of inertia about the center of mass. We've already given that the value I, times the angular acceleration. Okay, so our second useful equation says negative RFF is equal to I alpha. I'm going to rearrange this a little bit just to make the system easier to solve later, but you don't have to recognize that this works yet. So I'm going to write this as I alpha plus R FF is equal to 0. And I'm going to divide both sides by R. So all we get is I over R times alpha plus FF. This is our second useful equation. And I'm just doing that because now we, to solve this as a system, it's easy to make this substitution. We could, but you don't have to start thinking about the system of equations yet. All you need to know is that we have this one useful equation from Newton's second law, another useful equation from rotational Newton's second law. We're going to get a third useful equation, and then we'll solve this system of three variables from three equations. Okay, so look at the variables. I just said there's three. The variables are force of friction, A, and alpha. We only have two equations, so it won't work yet. What's the last thing we know? Well, we know this is rolling without slipping, and we have a formula for that. So, and that comes all the way back from particle kinematics. And that says that the acceleration vector in this rotated coordinate system is equal to negative r alpha 0. So that's the acceleration of the center of mass. It has the same meaning as the A in our equations above. And this gives us our third useful equation, which is that I'm going to write this as alpha is equal to negative A over R. And now we have our three equations for three variables. And so I'm going to substitute equation 3 into equation 2. So if I take 3 and put it into 2, what I get is negative I over R squared times A plus FF is equal to 0. And my equation 1 is, so negative MA minus FF is equal to negative mg sine theta. And now I'm just going to add both sides of these equations to combine them. And the benefit of that is that these two things cancel out. It just gives you sort of a quick way to do this. So we have negative quantity I over R squared plus M, and this is all times A, is equal to negative mg sine theta. And if I rearrange this a little bit, we can multiply both sides by negative 1, get rid of the negatives. I'll get a common denominator here, so this is I plus mr squared over R squared times A is equal to mg sine theta. We're almost there now. We're just, remember, what we're trying to do is calculate A in terms of these other things. And so now divide both sides by the stuff in parentheses, and you get A is equal to mg R squared sine theta over the quantity I plus mr squared. Okay, so this acceleration A that has that magnitude is going down the ramp. So now we have an expression for the acceleration for a rolling wheel. We have the expression for the acceleration of an object sliding down with no friction. How do we compare these two? Well, the last step is we have now all these different expressions for the mass moment of inertia for different profiles of wheels. And so we'll plug those values in for I, and we'll be able to compare directly to the acceleration we got before. Okay, so let's say we're racing these things down the ramp. We have an expression for the sliding object that's just A is equal to G sine theta. And now we have a disk a sphere, a thin ring, and a thick ring. So let's figure out which of these would go down the ramp slower and faster. The disk has a moment of inertia of 1/2 mr squared. So plug that into our formula. The denominator ends up being, this I is replaced by 1/2 mr squared. So we have 3/2 mr squared in the denominator. And you cancel the m and the r squared. And we end up with an acceleration that's equal to 2/3 g sine theta. Okay, so the acceleration of the disk is 2/3 as much as the object that's just sliding down. Now the sphere, the moment of inertia for the sphere is 2/5 mr squared. So plug 2/5 mr squared in for I. That's 2/5 mr squared plus 5/5 mr squared is 7/5 mr squared. Again, the m's and the r squareds cancel. And you get an acceleration of 5/7 g sine theta. A little bigger than the disk, a little smaller than the sliding object. Now the thin ring. The thin ring has a mass moment of inertia about the center of mr squared. So the bottom here becomes 2 mr squared. The m and the r squared cancel, and so you get an acceleration for the thin ring of 1/2 g sine theta. And for the thick ring, so that one, so now this R, let me change this up here. Notice that this R outer is what we've been calling R. So I'm going to just change that to R. So our acceleration is m g r squared sine theta over 1/2 m times the quantity r squared plus r inner squared plus mr squared. And the assignment for today, you're going to just have to fiddle with that a little bit to figure out how to compare the acceleration of this to these other things. So I'm going to leave this out of the race for now. You're going to have to do that. It's really just manipulating variables and stuff. But so what's happening in the race of these things down the hill? The sliding object with no friction would be the first one down because it has the biggest acceleration. The sphere would be the second one. The disk would be the third one. The thin ring would be the fourth one. And the question is, where does the thick ring fit into the accelerations?